I'm Will Anderson. This is my presentation of my project, Comparison of 3 Wing Configurations in Ground Effect. So, right now, the aviation industry is facing somewhat of a problem. Aircraft are contributing to climate change, and they need to be more efficient to meet climate change goals. One possible way of meeting those goals is using something called a ground effect vehicle. Ground effect is a combination of two aerodynamic effects that occur when an aircraft is close to the ground, the combined result of which is an increase in lift-to-drag ratio, which increases the aircraft's efficiency. A ground effect vehicle is simply an aircraft that has been optimized to fly in ground effect, and that allows them to be much more efficient than planes, it allows them to be much faster than ships, and overall means that they can serve cargo and crew transport applications, at least in theory. Right here, we see two diagrams that help demonstrate how ground effect works. As you can see, a surface placed underneath the wing increases the pressure gradient across the wing, which increases the lift. And then having the wing fairly close to the ground also disrupts the wingtip vortex coming off of the wing. That vortex causes drag, so when it's disrupted, it reduces the drag, makes the aircraft more efficient overall. There are three types of ground effect vehicle: the Russian Akranoplan, we've seen here, and then the reverse delta and tandem wing configurations, which were made by German engineers. The tandem and reverse delta configurations are the most stable of the three. They're all somewhat vulnerable to running into things like surface deformations along the lines of waves, or like if it's flying above like actual ground, like a rock or something. And to my knowledge, there has not been a direct side-by-side comparison of all three types in terms of efficiency. So that was the question I sought to answer. How does ride flight influence each of the three types of ground effect vehicle, and then which of them is most efficient, which of them is capable of attaining the highest lift-to-drag ratio? I hypothesized that the reverse delta configuration would be the best overall because the wing shape appears to be able to effectively compress the air both horizontally and vertically, which I just guessed might make it a bit more efficient. So, to complete this experiment, I needed to make 3D models. I did this in Fusion 360 CAD software. I tried to keep as many parameters as constant across the models as I possibly could, including mean aerodynamic chord, with the exception of the tandem wing because it's got two pairs of wings and wingspan. I then printed the models on a Stratasys 3D printer, and then I lightly sanded the models in the second trial, but not in the first trial. So, for testing, I used 6.5mm increments on a small adjustable bracket. I put this bracket inside the Jetstream 500 wind tunnel. All the trials were actually conducted upside down because of how the test arm is placed in the wind tunnel. There's no easy way to get the model to use the actual ground as ground, so I just used the ceiling instead. Just because it's close to the wall of the wind tunnel, there was a boundary layer that was unavoidable, but that's hopefully didn't have too much of a serious effect on the results, and I'll get to that in the discussion. I measured lift, drag, and lift-to-drag ratio at each ride height per ride configuration. I took those measurements 3 times each, and I used a slightly different procedure for the second trial, which I'll get into later. And then for all graphs that you will see, all of them will have error bars with representing 2 times the standard error, and that's what I used for data analysis. So the second trial, there were some inconsistencies in the first trial, so I thought that running a second trial would be a good idea. I used a better bracket, one that held the model a lot tighter. I also checked the angle of attack between each data point, and I also was able to use slightly smaller increments, only 2.5mm this time, because it took longer to check the angle of attack between trials. I only did 3 ride heights instead of the original 5. So, results. Starting with trial 1. Lift data, there's no discernible patterns to be found here. It's basically a complete mess, very inconsistent. Drag data, on the other hand, there is a consistent pattern. As you can see, there is all 3 of the configurations have a positive slope, and of the 3, the tandem wing has the highest slope and the reverse delta wing has the lowest slope. The lift to drag ratio is calculated from the lift and drag, which means that most of the inconsistencies in the lift data carry over, and that means that, again, no really discernible patterns can be observed here. So for set 2, there are a few things to note here. First of all, probably glaringly obvious is that, especially at 2.5 millimeters, the inconsistency was pretty terrible, especially for the tandem configuration in red. However, there is a small but inconsistent pattern in that the reverse delta configuration is always slightly better than the other two on average. However, this difference is only significant at 5 millimeters. It's not significant at the other two ride heights. For the drag data, we see very tight groupings, very much unlike what we saw in dataset 1, which is somewhat unusual. So there is a pattern of a significant decrease for all 3 points, and then a slight increase, which is only significant for the ecranoplan. It's insignificant for the other two configurations. And then the lift-drag ratio, again, it's calculated, so the fairly small patterns observed in the drag data don't have a huge amount of influence on the results here. It's mostly just the inconsistencies of the lift data that drive this point, or this graph. So, discussion. For dataset 1, overall, the inconsistent data basically mean that there is no way to draw conclusions relating to the research question from this dataset. However, it does seem likely that ground effect was demonstrated just from the drag data alone. That's because, while a increase as ride height increases could also be explained by boundary layer, the fact that the tandem wing was most affected, that the slope was the highest, that fits with what would be expected if span ground effect was present, which overall means that there was probably ground effect demonstrated in this experiment. The inconsistency in the lift data, I believe, can be explained by the angle of attack not being checked in between trials, and the fact that the model could rotate on the bracket slightly. It's also possible that the bracket could have rotated relative to the test arm, but I don't think that was as significant a contribution to the inconsistency in this trial. So for step 2, I attempted to remedy those issues, but ultimately there was still very inconsistent lift data, and the decrease to increase pattern in the drag data is not promising at all. That's not what would be expected, as explained earlier. So I think it's possible that the new and improved bracket, just because it's so much larger, might have had an influence on the aerodynamics. The insignificant pattern observed in the lift and lift-to-drag ratio data does indicate that the reverse delta configuration may be best, but the fact that those differences aren't significant suggests that that can't really be used to answer the research question with confidence. I'm not comfortable drawing any large conclusions from that. And overall, the bracket solution didn't work. That's because the bracket was actually still rotating, as I found when I had to adjust it repeatedly, relative to the test arm, just because the test arm wasn't meant to handle the kind of torque that the adjustable bracket was putting on it. So overall, I don't think this method of analyzing ground effects is especially practical, and something like computational fluid dynamics software may be a better way of answering the research question. These are the references I used in this presentation. Thank you for watching.